So, we will continue here. So, we made this table for various angles of heel, and we have G 0 Z 0. Now, note that in real case, in reality, when the ship is really heeling, I told you that the GM does not remain constant, G does not change. Let us suppose that the ship is without any change in the mass, there is no change in the weight anywhere. So, G does not change for the ship, whatever it heels or does not heal, it does not matter. But if it keeps healing due to other reasons without the change in weight, if it keeps healing, actually that M will keep moving, okay? It will become an M curve. But note that in these derivations completely, we are assuming that M does not move. Why I say that is, in that healing curve, I mean in the GZ curve, we have one value of GM. It is one value of GM for the whole angle of heel starting from 0 to 90 degrees, angle of vanishing stability. The whole thing, there is one value of GM for the ship. That means the meta center has not shifted at all. So, that actually is a very important point that you have to remember in this, okay? Because it has implications. For example, you look at this table, it says G 0 Z 0 at different angles of heel, phi 1, phi 2, phi 3, like that. Now, if you want to get GM for the ship, how will you get initial GM? You just have to divide it by sin phi. GZ divided by sin phi will give you GM, okay? So, when each of them are divided by, like the GZ value here, when you divide it by sin of 15, you will get some value of GM. It should be the same value that you are getting here, means sin I mean GZ at 30 divide, what I mean is, is it clear? This will be equal to GM. Of course, at 0 0 it is not defined, it becomes 0 by 0, it is not defined there. After that, everywhere you are getting, this should be equal. If you want, you can check it, it should be, okay. In this problem it is, there is we have seen it is true, but in case you have a problem where that changes, then you have a serious problem. It is not going to be solvable using any of these methods. So, forget those kind of problems, we are not doing that, we are only dealing with simple problems in which GM remains constant for the whole angle of heel, means there is no M curve, M is fixed, it keeps rotating, but M remains there only, nothing changes, that is the meaning. So, how do you get G 0 M 0 for this ship? G 0 M 0 means the initial value of GM without the shift in the center of gravity, okay. First there is a ship with some kg, to it some weight has been added at some height, as a result of which the kg has risen by some amount 0.25 meter. So, there is a G 0 G 1, and as a result of which when it starts healing, you have different values of GZ. Now, GM M 0 means the value of GM before the weight has been added. So, G 0 M 0 will be given by G 0 Z 0 by sin phi, that means like this, it is just that it is G 0 Z 0, that is all. So, any of these will give you G 0 M 0, you take any of these and all of those G 0 M 0 will be same, in this case it is. So, you will get G 0 M 0, and very straightforwardly you can get G 1 M 1, that is instead of this G 1 Z 1, if you G 0 Z 0, if you take G 1 Z 1 and divide by sin phi, you will get G 1 Z 1 at some angle phi, you divide it by sin phi, you will get your G 1 M 1. So, this is the first question, this is one of the questions, that is you are asked to find GM, that is the fourth question. Then you have this table now. Now, the another question is, what is your maximum GZ initially and before, after the ship or in the final condition, what is your maximum GZ? All you have to do is look at this table, you have GZ as a function of phi, look at the maximum value of GZ and you find out what is that phi corresponding to that, okay. Of course, if the value is in between, interpolation and all is there, you have to draw the curve and you have to get that. That is why you have to draw the curve anyway in these cases. That is why I said to get the maximum values, you have to draw the curve, and from that
So, it will be on whenever the
wherever sin phi is maximum, GM will be, GZ will be maximum. Um, yeah, that seems a strange logic. Something I have made wrong here. Wait, G0 Z0 is equal to, it happens when phi is maximum. Actually, I told something wrong here. Estimate of the GM actually it does. Any of you have a calculator? Actually, that is a very good point you have raised. I think I have told something wrongly, that is just checking one thing. Oh, how do you, okay, on 0.391 divided by sine 15 sine, actually I am not able to use this. I will tell you, you do it. Okay, that is do 0.391 divided by sine of 15 degrees. 1.51. Okay, do 1 divided by sine of 30 degrees. Oh, okay, sine of 30 degrees is 0.5 now. So 1, that is 2. Oh, so I, all right, then actually I told you wrongly, that assumption is, so I really told you a wrong thing. That is what he said, pointed out a very important thing. GM is not constant here. Okay, GM is varying here. So GM is actually varying with, it's like the M curve, it's with the M curve. GM is not constant. So that GM that you are plotting is G0 M0, which means at the value of the first angle of heel, right? That is, we can say it's at 0. So it's G0 M0 is actually your GM at phi very close to 0, like let's say 1 degree or something. The GM when it is at that point, okay, that is your GM that you are getting here. Of course, in the derivation itself we saw that you will have, it comes like this, GM at phi equal to 0. Okay, that means it's GM at phi equal to 0. So yeah, right. Okay, so GM is actually varying. That means it's GZ is maximum not when phi equal to maximum, because GM is also varying. So GM sin phi, GM also varies, F phi also varies. So GZ occurs at some intermediate value. Otherwise, it does, it's a good thing. It doesn't make sense. So actually, as I, that what I checked here was just this GZ divided by sin phi. It's not the same. GM is changing. So GM is changing. That means G is fixed, because I am talking about the case when weight has not been added, that is G0 Z0. So weight is not added, that means G is fixed, that means M is changing, M is moving in an M curve. So that assumption is not made, it's, sorry, it's a mistake. And G mem that you are measuring there is at phi equal to 0 at the initial value. Okay, okay. Therefore this gives you G0 M0. So what did we get? You get it to be some 1.26, and you see that in the G0 Z0, in this G0 Z0 curve, you see that your value of G0 Z0 becomes negative after a value, that is at phi equal to 78 degrees, the value becomes 0, Gz becomes 0. Therefore, the angle of vanishing stability, the angle of vanishing stability is at phi equal to 78 degrees. I think there is a maximum or the max range, you are asked the range of stability. Range of stability means the phi starting from 0 to where gz becomes 0, means in this curve starting from phi equal to 0 to phi equal to this value. Okay.
So in this case, how do we find G0 M0?
Why?
So because
No, at 0 you cannot put it, will become 0 by 0. That's what you are asking. It is a value slightly after that. You take, means you take some point slightly after 0. At 0 it's undefined, you cannot do it. Slightly after 0, it's up to you. In case you are getting 1.26, maybe you will get, other person will get 1 point, not very different, 1.3 you will get. That is okay. That small difference, don't make it too far. When you are taking the graph sheets, take the first point close to 0, means you first point in this case is 15 degrees. So from 0 you will connect to 15 degrees, let us say like this. Let us say the gz curve starts like this and it goes like this. Now this is 15 degrees. Let us say that the graph sheet is like this. You take the first point, okay, somewhere here, what is your GM that you take, otherwise you cannot do it, it's not defined. Okay. Then what was I doing? So we found out, okay, I was telling you about the range. So this is phi equal to 0, this is the angle of vanishing stability. So this is known as the range of stability. So this, according to this problem, comes at 78 degrees. This whole thing is 78 degrees. That is where your stability vanishes to 0 at that point, and then you are asked the maximum Gz and the value at which that maximum Gz occurs. So that is just a matter of reading from that graph. You have the graph, you look at the graph, see where the Gz is coming maximum and the angle at which it is coming, you just read from that. Then you are asked also dynamic stability. You have heel. So to find dynamic stability, note that you have to do the area of the Gz curve. That means you have to do this, let us say Gz, then you will need the same concept of Simpson's multiplier. So as you can see, the Simpson's multiplier concept you need everywhere, you have to know that very clearly. So you write like this, so Simpson's multiplier 1 4 2 4, then so the function of area is just Gz into Simpson's multiplier 0, 0.24 into 4, 0.96, like that, and you find the sum sigma function of area, and finally you do h by 3 into sigma function of area will give you the total area under the Gz curve. It will give you the area under the Gz curve, and okay, so therefore you are getting, now you multiply this with delta, the weight of the ship, that will give you the dynamical stability, that is your dynamical stability. Then of course you are asked the dynamic stability in the initial case and dynamic stability after the kg has been changed. So the same areas you have to put, I mean you have to, the same way you have to do, but this will become initially G0 Z0, in the next case it will become G1 Z1. So this is the initial and final. So you have this is how you find the dynamic stability. Okay.
Sir, how can we find area at up to in between angles, means suppose area at 40 degree or area at 20?
That's what you have to take up to that angle, area up to that angle, means you are saying if you do not have the value,
Yeah.
that means you have to read from the graph. That's why I said you have to draw the graph first. That means you are asked the dynamical stability up to what? Dynamic stability, you are asked the dynamic stability at 40 degrees in this problem. That means you have to find the area up to 40 degrees. In this case, it is not a problem because you are given the Gz value at 40 itself. But if you are given there are some problems coming up where you have to find Gz in between values, means you have to find the area up to some intermediate values. That means you have to draw the graph, you have to find the value of Gz at that angle. You can do like this. That means first of all you need h as a constant in Simpson's multipliers. That means you will have to divide it into equal number of parts. each of those values you have to read from the curve and then you have to do it. It's a laborious process, but that is the only way to solve the, because you cannot do with variable edges. We haven't done that kind of problem, right? If you have a constant edge and this, suppose you have to do still some 32 degrees or something, it becomes slightly complicated. You have to 32, you have to divide, let us say this becomes 24, then you have to do 16 and probably 8 like that, and 0, 8, 16, 24, 32 like that it will become, and that no other way but the GZ has to be read from the graph. So, you will have two GZ curves, one is a G0 Z0 initially, then the weight is shifted and the center of gravity is shifted, and you will have G1 Z1, and based on that you will have the initial dynamic stability, final dynamic stability. Okay. One more problem, that is, it says that this is about a horizontal shift. The problem shows a horizontal shift of weight. You are told that there is a vessel which has a displacement of 12,000 tons and it has a kg of 7.64 meter. Now, again you are given the GZ table. So, like this you will have at least one problem like this for a mid semester, where you have to draw a GZ curve. So, you have to know how to do this. So, 0.19, 20. Of course, you can connect it very in a simple fashion, freehand, very do it quickly. I mean, you have only 1.5 hours after all for mid semester. So, quickly if you can do this 0.5. So, you have like this, like this it goes, and at 70 it becomes almost 0. So, around 70, after 70 it is becoming the angle of vanishing stability. Now, you are told that cargo is redistributed as a result of which the center of gravity shifts 0.13 meter to port. Okay. You have said that the center of gravity shifts 0.13 meter to port. Now, you are told as a result of this find the heel, means this has been shifted, as a result of which find the heel angle, also find the dynamic stability from that heel angle to angle of 30 degrees. This is one of those where you have to, obviously you are going to get the heel angle in some 11-12 degrees something you will get, whatever you get from there you have to find the area up to 30 degrees. Okay. That means couple of things. First, you have to obviously draw the GZ curve, you have to find the initial heel due to the shift of weight, and finally, you have to find the dynamical stability. So, three things, you have to first find the initial heel due to shift of weight, then 2 you have to find heel, you have to find the area under the curve. One more thing you have to find, now what is it, is there, and yeah, basically you have to find the dynamic stability. You have to find the dynamical stability from that angle of heel to 30 degrees. So, two things you are asked to find in this. Now, what is a way to find out the heel? Do you remember some way of in which we have found the heel? Actually, we did something known as an inclining test, if you remember. Okay. An inclining test was described as, let me go back to that, page 130. We will go to the inclining test. Okay. We have done an inclining test in which, if you remember, we hung a pendulum at the top, somewhere you hung a pendulum, and a weight was shifted from one point to another point, as a result of which the pendulum, the vessel heeled, pendulum is at an angle, and when the vessel, when a weight is shifted, that means G is shifted. So, when that happens, you have to find your question, from the angle of heel you have to find GM. So, this becomes in the other way around, you have to find the angle of heel because of a shift in weight, actually the final, I am not going to do it again. The final expression is G0 G1 is equal to W into D by W. Okay. This is your shift in the G0 G1 as a result of the shift in the angle of due to a weight W shifting through. Is it given how much cargo is redistributed? Let us see. You are given 0.13 meter. So, you are given G0 G1, this you are given, then you have GM. Now, GM, okay, that is the second one you need. Now, this is another thing we had, G0M, another formula that we had, R0, actually you won't know what is R0 because without looking at the figure, but R0 by RS into W, I will write this as G0 G1. Note that we are told that the center of gravity of the vessel is shifted. This problem says that center of gravity of the vessel is shifted 0.13 meter to the port. So, you are given G0 G1. So, you have this one. Then you are told, now what is R0 by RS? R0 by RS is equal to tan or cos R0 by RS. It is equal to R0 adjacent by, it is actually cot phi. Okay, it is cot phi, if you remember, it is cot phi into G0 G1. Okay. Now, how will you get G0 M? It is this what I told you. You have to get G0, you have the G0 GZ curve you are given. Okay. Here you have the GZ, means in this problem you are given the GZ curve. From that you have to get your G0 M. As close to the origin as possible, you find G0 M. Okay. And or G0 by sin phi you do, and that will give you G0 M. Okay. And so, once you get G0 M, you know G0 M and you know G0 G1. G0 G1 is just the shift in the center of gravity, it is given in the problem. So, this you know G0 M you get from the curve, from that you have to find cot phi. Okay. Therefore, from that you find phi, that is your angle of heel. Is it clear? You want something? Okay. All right. Therefore, this problem gives heel at about 7 degrees. So, actually you will be solving for cot phi, and that solves for phi to be 7 degrees. So, that means because of the horizontal shift in the center of gravity, the ship has heeled through 7 degrees. So, it is like this now. Now, now you are asked now you can do two things. First of all, if it is asked, you can find the new GZ curve. Remember, this is the GZ curve without the shift in the center of, the moment the center of gravity shifts, finally you will have a GZ curve. That GZ curve is G1 Z1. So, you have your G0 Z0, 0 point, like 0, let us call this heel, 0, 10, 20, 30, like that, G0 Z0, 0.5, like that you will have. Then you have to do this. I have derived it. I saw that I told you that G1 Z1 becomes G0 Z0 minus G0 G1 cos phi in case of horizontal shifting. In case of vertical shifting, it becomes sin phi. So, this is 0, whatever G0 G1, whatever it is not 0, minus 0.13, 0.13, 0.12, it becomes like that, and G1 Z1 becomes G0 Z0 minus this. So, this becomes minus 0.13, this is not 0 actually, sorry, this is 0.19. Anyway, this becomes 0.06. So, like this. Okay. So, from your G0 Z0 you subtract G0 G1 cos phi and you will get your G1 Z1, that is your new value of GZ curve. So, you have your old GZ curve, you have your new GZ curve, then The second part of the problem says you find the you have to find the dynamical stability from that heel angle to an angle of 30 degrees. So, you have your final GZ curve. Now, dynamical stability, there is only one way, you have to do it this format only. Simpson's multiplier and function of area. So, you will have like this 10, 20, 30 like that. Now, note that in this problem you have to find area from 7 to 30. So, this is data is given as 10, 20, 30. There are two ways of doing it. The first one is you have your GZ curve, this is your G1 Z1 curve, you have your GZ curve, you can take the curve, start from 7, 7, 14, 21, 28 like that, but it becomes slightly difficult. So, a better thing actually is you do like this 10, 20, 30 we have the values, you find the area till that, then that means you have to add the area from 7 to 10 now. Okay. 7 to 30 we have to find, 10 to 30 you can find using this, and 7 to 10 you have to find now. So, that is maybe easier in this I think than doing 7, 14 doing that continuously. You split it, split the areas, you split areas and you get 10 to 30 using this format. It will be very easy using this because you already have the values, it can very easily do this. Then from 7 to 10 you get the values and do it. Okay. That means you read from the graph and then you, of course, these in this case they have done in a different way, that is I will just show what they have done. You can do this also, but I do not think you will get a big error. So, this is your GZ curve. It is not this one. Okay, they have not shown. Actually, what will happen is that you split what they have done is same thing, 10 to 30 they have found the area. Now, to find 7 to 10 you will have a small area, you can do like this, that means it will come an area like this. Okay. You will get an area like this, okay, 7 to 10. Now, one way to do it is just assume it is a triangle, okay, and you find the area. You do not do the Simpson's multiplier, just half base into altitude, half base into altitude. So, how will you get the base? Base is just 3 degrees. So, that is 3 divided by 1 degree is equal to how many radians? Whatever, pi by 180, no? What is it? 57.3 anyway, I think will give you. 1 radian is 57.3 radians. So, 3 degrees. So, 3 by 57.3 into altitude, that means you have to find the value of what is this? F of 10 exactly. What is it? F is what? Oh yeah, it is GZ, that is what I am asking. F of F is actually GZ. So, you find the GZ at 10, GZ at phi equal to 10, that is all. This is one simple way of doing it, and if you have an area, if you have a angle less than let us say 5 or 10, that is what you can make it more and more complicated, that is up to you, but
at 7 there would be some GZ.
At 7 there will be some GZ according to them. Okay, it is better to look at it as a trapezium. Okay, that also is yeah, it is better to look at it as a trapezium, I guess. Yes, actually they have done that. I think it would have been better if they had taken it as a trapezium. That is correct, because it is actually a trapezium, because there will be some value of G z at this also. Do that. It is better to take it as a trapezium. So, you have like this. What is the area of a trapezium? Half this plus this divided into this. Okay. So, its vertical distance again becomes 3 by 57.3 into G z of 7 plus G z of 10 by 2, right, something like this. Okay. So, this will give you the area of the trapezium. I think this is what you should do. Actually do this for the exam. I mean, there is no point spending too much time on Simpson's multiplier. It makes it very complicated. You will spend a lot of time on it. Best thing is you see if you can, means whatever is the you will have a GZ data given at as 0, 10, most likely in steps of 10, 0, 10, 20 like that. So, you find the area, that closest area, let us say 7 to 30 if you are asked to find, you obviously see that 10 to 30 can be found using that value. So, like that you look at it and divide it, and then 7 to 10 only you have to find. That means only a small area is left. You just find a use the trapezoidal method, that is this trapezium area you find out and you substitute that. That will give you the, that should give you the exact value. And because you are, if you see this value is just it becomes like this, the 10 to 30 area is about 0.14 ton radians, meter radians, and the other one is 0.001 meter radian between 7 and 10. It makes no difference. If you do the Simpson's one, probably you will get 0.002 maybe. It won't make any difference to your answer. Okay. So, so just do this. This is easier. Okay. Now, we come to a another, what happened? Yeah. Okay, you have another kind of problem in which you have a grain, you have bulk carriers. Okay, there are something known as bulk carriers. These are huge ships, size of 350 meters probably, and very broad and very large ships, and these ships carry material in bulk, things like ore and means not liquid, but it is liquid like material. Grain means the material moves like a liquid only. So, that is the thing about wheat or things like that. Okay. So, all these things, what we do is we use the same concept as liquids, because these things move in the same form as liquid. The shape of the free surface will be like this, and the shape of the free surface goes when the ship moves, it will go like this. So, it moves just like a liquid. So, if you remember, we have already done a free surface effect for ships. Same thing holds here, free surface. So, for grains or grains, it is also container ship. That these are the two type of ships, container ships and bulk carriers. These we use this concept of a free surface effect, and in this case, what will be G0 G1 means this is a shift in the center of gravity of the whole ship, which will be given by So, this is the basic definition of the change in G due to a change in due to a movement of mass inside the container. So, you have G0 G1, the shift in the center of gravity of the whole ship is equal to weight of grain shifted into distance shifted by displacement. Now, you write this as lambda 0 which is equal to, Okay, in this case of grain, in this particular case of grain, we call this as lambda 0, and it is G0 G1 only. G0 G1 is equal to lambda 0, and it is written in a slightly different form. That is your lambda 0 is equal to G0 G1 can be written as something like this. The numerator is equivalent to a quantity like assumed volumetric healing. This is a term, it is a particular term, it is called VHM. Okay. Note that this VHM is defined only for this, either for liquid or for ores. So, either for containers or for either for ores or grain, mainly for grain. So, in this book it is defined as grain. So, it can be anything that moves as a liquid. So, a grain, it can be, it is true for liquid, and so this thing is called as a volumetric healing moment. It is something like the weight of grain shifted into distance shifted. Weight of grain shifted into distance shifted is what you call as volumetric healing moment, and it is divided by something called a stowage factor into displacement. Stowage factor is not that important here, it is something like VHM divided by displacement. Okay. So, this volumetric healing moment is important, because in the problems of grain or container ships, you will be directly given the volumetric healing moment. You will be told that VHM is so much, because that is a particular value that they measure. It is something like the weight of grain shifted into distance shifted. So, that is VHM, that will be given as a quantity to you. So, you have to know what it is. So, lambda 0, which is equal to G0 G1, is equal to VHM divided by this. So, you have lambda 0. Now, you will see that now actually okay, lambda 0 is okay. Lambda in general is defined as G1 cos phi. Okay. Therefore, lambda 40 is equal to G0 G1 cos 40. Cos 40 is 0.8. So, lambda 40 is equal to 0.8 lambda 0. Okay. Lambda 40 means the value at the phi equal to 40, at the healing moment equal, at the healing angle equal to 40, what is the value of lambda? This is at lambda 0, which means it is the value at 0, which is G0 G1 cos 0, which is G0 G1, and lambda at 40 becomes G0 G1 cos 40. Lambda in general is G0 G1 cos phi. Okay. So, these are some terms used for this grains particularly. Okay. Now, let us do one problem related to this. It is actually a ratio. Actually, I will tell you, yeah, that is, suppose you have a grain, you have a shape like this. Okay. Now, you can have two, in general we split this into two particular cases. Suppose that grain is filled up to this, okay, they have drawn it like this. Okay. When suppose it is filled up to this height. Okay. Therefore, stowage factor will have some value. Okay. And suppose it is filled up to this height, stowage factor will have some value. It is something depending upon the amount of free surface and the amount of fixed surface. It is a ratio that depends upon how much of the volume is free and how much of the volume is occupied. That is called a stowage factor. Stowage means storing factor, how much is stored, that is the meaning of stowage factor. The exact values of stowage factor will be given in the problem, because you cannot calculate, and that is too difficult. Of course, it is not too difficult, you are if you are given the shape, you can calculate, but I will give you the stowage factor. So, we can see what will be its unit. It's actually, let me see, healing moment. I think its unit will come as ton per meter cube or something, meter cube per ton. It's a value that depends upon the amount of space that is left and amount of space that is occupied, okay, meter cube per ton. Then okay, then let's look at this problem. You are told that there is a vessel that has a displacement of 16,500 tons. You are told that it has a kg of 7.5 meters. Now, all I can say is you have to look at the problem. If it says it is to deal with grains, and then you will be given the volumetric healing moment and all that. If it is, actually we have covered a lot of variable sections, means horizontal shift of weights, vertical shift of weights. I have said, I mean, I'm even just in this section I have carried out different types of problems where you have a, so looking at the problem, it's not easy to figure out what you are dealing with. A lot of formulas to remember. It's true, but this is one particular component which you have to, I think, by heart only. You see that where there is grain coming, you use this part. It's like this. I mean, the formulas have been derived for each particular case. You will see next we are going into wind healing moment. That is a different thing. So, for container ships, they have a particular set of rules, and a set of rules have evolved in their fashion. For we have seen free surface effect in liquids like oil tankers and all that. There is a set of rules, and those rules, it keeps evolving in a different fashion. So, if you are doing a problem in that, you will have to use the terms in that. You will have to, it will be different from the terms in the grains. You just have to by heart it. There is no other way. So, this problem, it says that it's about grains. It says that it's a container ship which carries grains. It says that the grains have been grains shift in the ship, as a result of which you are given some data are given. You are given VHM, the volumetric healing moment. Then you are given the stowage factor as some 1.2 meter cube per ton. Then you are given the GZ curve or GZ table, in fact. So, heel versus GZ 0 0 15.267 30.645, like that. You are given the GZ curve, GZ table here, and around 75 degrees it becomes negative. So, you have the vanishing stability at around 70 degrees. Okay. Now, first thing you have to calculate is your lambda 0, which is G0 G1. Lambda 0 is equal to G0 G1 cos 0 is equal to G0 G1 is equal to volumetric healing moment divided by displacement into stowage factor. Okay. This I think all of them are given. VHM is given, displacement is given, and stowage factor is also given. So, from this you get lambda 0 is equal to 0.2 and lambda 40 equals 0.2 of 0.8 of this, which is 0.16. Should have been 0.16, but they have got 1.16. That is not correct. 0.16 meter. So, it should be 0.16 meter actually. Actually in this book, unfortunately, there are a lot of spelling mistakes and errors, lot of errors are there. So, you do not get confused, there are mistakes. So, this you get. Then what are you asked in this question? You are asked to find first of all you are asked to find, because of this what is the heel that is produced as a result of this volume because of this grain shift. You are told that there is a grain shift, and we have calculated the grain shift. What is the shift in this? Remember, this lambda 0 implies G0 G1. G0 G1 is a horizontal shift in the center of gravity. Okay. So, lambda 0 and G0 G1 represent a horizontal shift in the center of gravity, as a result of which there will be a heel. Now, that heel you are asked, that is the first part, you are asked what is the heel. Now, how will you find the heel? Same formula, inclining test, that formula. Okay. You just have to find your GM, G0 M from the GZ curve or G0 Z0 curve. Then you get lambda 0 you have got, which is your G0 G1. From that you will get your G0 G1 and GM G0 M, you will get your cot phi or tan phi, and you have to get your phi. This method, I mean, this is the way to solve it, and that is the first thing. You are asked what is the heel. Then so that comes out to about 12 degrees in this case. So, the initial heel is 12 degrees. Then your next question is, find the dynamic stability up to this starting from this angle of heel up to 40 degrees, means dynamic stability from from this angle of heel, that is 12 degrees to 40 degrees. Okay. So, 12 degrees to 40 degrees you have to find the dynamic stability. We will use the same method. You do one thing, you find the area from 20 degrees to 40 degrees, or what is it given in steps of 15. In this problem, it's actually GZ table is given in steps of 15, or is it 15? Oh, then you cannot find from 20 to 40 also. Then I think the best thing is to do the Simpson's multiplier only. You read the GZ values and read the from that you find the value of GZ for each of those, and you find the area. There doesn't seem to be any other way, because 12 to 40 degrees it's given in steps of 15, 30, 45 like that. So,
20 to 40, 20, 30, 40, and so 12, 16, 20,
20 to 40, the problem is from graph, if you are reading it, you can as well do it straight. No, 12 to 40 you divide it into, there is no point in it, there is no point doing it twice. So, you have to read from the graph, there is no other way. So, better to just read it and divide it into 12 to 40. You it's actually very difficult, because H, how will you make it uniform? You have a distance of about 20, how much is it, 28, right, 28 degrees difference. You will have to divide it into a couple of points and do it. Yeah, maybe in 7 steps of 7 you can do it. Yeah, 12, 19 like that you can do and come up to 40. Yes, that is better. Now, the next question is, are these values of GM, heel and dynamic stability satisfactory? I will tell you what we mean by satisfactory. That is, there are some rules as far as grains are concerned. It is like this, that is, now the first rule is that you have to by heart these rules. Okay. So, before this I did some rules regarding what was it, about the dynamic stability. Some area should be less than, should be greater than, GZ should be greater than, like couple of formulas, it should be less than some 0.03 meter radians or something I said. So, those rules you have to remember, but when it comes to grains, do not follow those rules. It is like you have to just attend the class only, there is no other way you will know. So, you have to, do not follow those rules. If you are asked if does it satisfy the stability requirements, do not go to those stability requirements, they are wrong, they are not meant for this grains. So, when you are said grains, these are the stability requirements, that is first one is that the angle of heel due to the shift of grains, angle of heel due to the shifting of grains should never be greater than it should never be greater than 12 degrees. So, in this problem actually we got 12 degrees, it's like the marginal case, it's okay, that is pass. Anything greater than 12 degrees is fail. So, it should be angle of heel should always be less than or equal to 12 degrees, that is the first condition. So, that means that you have the ship, whatever happens, how there is a maximum level to which the grains can shift, okay, because it is full, means it cannot shift, all the grain cannot shift here because it cannot get compressed like that. It will shift a bit, as a result of which G will shift, because of which the ship will heel a bit. This heeling should never exceed 12 degrees, that is the first condition. Then that is the first rule. Then next is the area between the area should not be less than 0.075 meter between okay, this is one thing I will have to explain. Anyway, the area between the or writing arm is called GZ. So, the area between the heeling arm curve and GZ, I will tell you what is the heeling arm curve. Okay, I think they were the middle, actually it will take some time. So, the area between the heeling arm curve and GZ, area means the area of the dynamical stability, means the dynamic that should, it is not the dynamical stability is delta into area. So, the area itself they are saying should never be greater than, or no, it should never be less than, or it should always be greater than or equal to 0.075 meter radians. I will explain now what is the area that they are talking about. Now, let me draw the GZ curve. Let us assume this is the GZ curve for that grain, I mean this is GZ, this is the GZ curve for the grain case. So, now we have seen that there is a G0 G1 coming, means a shift in the center of gravity, as a result of which it is heeling. Now, that G0 G1 is like a heeling arm, okay, that is called as a heeling arm, that is what is causing the heeling. So, that is called a heeling arm, it is lambda 0, it goes from lambda 0, it goes, that heeling arm is actually changing, heeling arm is G0 G1 cos phi, this is your heeling arm, okay, it goes from lambda 0 to lambda 40. So, your this is lambda 40, which is 0.8 lambda 0, lambda 40 is cos of that. So, something like this you will have a heeling arm, this is lambda 0 and this is lambda 40. Okay. So, what is your heeling arm? Just remember this, heeling arm is the arm that is causing the heeling. Okay. This is what is causing the heeling, and therefore, this now what they are saying is that the area between the heeling arm curve and the writing arm curve means which area? This area. Let us say that up to 40 degree, this is 40, this area. The angle, the area between the heeling arm curve and the writing arm curve, between the angle of between 12 degrees, let us say 12 degrees, this is, let us say this is 12 degrees in this case, or maybe it is 12 degrees, and from that up to it does not have to be exactly this, okay, this, let me, this looks confusing, 12 degrees can be, I will put this to be 12 degrees, somewhere is 12 degrees, it is now from 12 degrees from here, from this point. So, this area is what I am talking about, this area should be greater than or equal to 0.075 meter radians. So, that means you have to find this area. So, what is the way to do that? You find integral g dz from between these two values, that will give you this whole area minus the area of this trapezium. Okay. Between this, that means you have to find lambda at 12, lambda at 12 you have to find, you have lambda at 40, you find the area of this trapezium, subtract the area of trapezium from this, you will get the area that we are talking about. That area should be, okay, I will stop here. that area should be greater than or equal to 0.075 meter radian is a condition for stability. There are some more, but this is the main thing. Okay, thank you.